Welcome to the status update from the RISE-6G project. My name is Henk Wijmers from Chalmers University of Technology, and I'm the Work Package 5 leader, where Work Package 5 deals with RIS for enhanced localization and sensing. This will be the outline for today. I will first cover some basics of our work package, followed by a primer on the use of RIS for localization and sensing. Then I will move on to some highlighted results from the work package, as well as our outlook. Here is Work Package 5 in a nutshell. The main question we try to address is, by the introduction of RIS, if we can have better localization sensing performance than without RIS. And here better is measured in terms of different KPIs, including the accuracy, availability, latency. Our work is broken down into two tasks. We have task 5.1, which deals with architectures, deployment strategies, and control methods. And task 5.2, which deals with methods for estimation and detection to perform localization as well as SLAM. In our work package are the following partners: CEA, NEC, Chalmers, Aalborg University, University of Athens, and CNIT. Let us now have a brief review on the use of RIS for localization and sensing. In this slide, I will present the localization and sensing without RIS. So when I talk about localization, I mean the same as positioning, which is the determination of the location of a connected device, a UE, based on uplink or downlink signals. This positioning can be done on time-based measurements, for instance shown on the left, based on round-trip measurements, which constrains the user to lie on the intersection of circles. It can also be done based on angle measurements, for instance here shown in the middle, based on angle of departure measurements, which constrains the user to lie on the intersection of lines in 3D, or any combination of the above. Localization has its role in the 5G architecture, which is shown in the figure with the access and mobility management functions, as well as the location management function. So all in all, positioning requires a number of things to be present. First of all, reference nodes with non-location orientation. So these are typically the base stations. Synchronization between those reference nodes, pilot signals in uplink or downlink, and then measurements from the radio signal, as well as fusion of the measurements to compute the user position. And all of this should be supported by the architecture and adequate control signaling. Positioning and sensing have their own performance metrics, including accuracy, latency, and availability. In addition to localization, we're also considering sensing, which refers to the detection and estimation of changes or events in the environment based on the radio signals. So positioning can be seen as a service on top of sensing. We can distinguish between radar-like sensing, where targets are detected and their parameters estimated, versus non-radar-like sensing, such as activity monitoring or channel sensing. Let's now see what happens when we put the RIS within the localization context. In RISE-6G, we consider a wide variety of RIS, but for the sake of conciseness, I will only consider here reflective RIS and hybrid RIS. So reflective RIS can take the incoming signal and direct it in an arbitrary direction, while a hybrid RIS can do this and also locally process the received signal. A RIS can both enable and boost localization. Enabling means that we can provide localization service that would not be possible without the RIS, while boosting just means improving the existing localization service. And the RIS can act as either infrastructure or as a device to be localized. If it's part of an infrastructure, of course, its position orientation need to be known. To integrate RIS into localization and sensing, there are a wide variety of problems that need to be addressed, including architectures, RIS control strategies, methods for localization and sensing, as well as measuring the attainable performance based on synthetic and real data. Let us now move on to some of the results from Work Package 5 in RISE-6G. In task 5.1, we've developed different architectures related to different scenarios. We have localization and sensing scenarios with and without base stations. In some of these, the RIS acts as part of the infrastructure, while in others, the RIS is to be localized. For each of these architectures, we've also defined this data flow and signaling. I will not go through all of these, but focus only on one. So here is an example where we try to localize a single antenna user device with help of a single antenna base station using RIS. Without RIS, in this case, you would need 4 base stations, but with RIS, you can remove 3 of those base stations and replace them by RISes. To perform localization in this context, you need 1 or more RIS with known time-varying configurations. You need to know where those RISes are, both in terms of their location and orientation, and you need some kind of synchronization between the user and the RIS. This then reflects in the architecture, which is shown in the figure there in the middle, where we see the location management function, the access and mobility management function, but in addition, we also see a RIS orchestrator and a RIS controller. A RIS controller controls an individual RIS, while a RIS orchestrator operates at a slower time scale and coordinates the activities of several RIS controllers. The figures in the bottom show the data flow, so this represents the messages that are sent between the different entities, logically or physically. In terms of RIS control, we've looked at a variety of RIS configurations or beam patterns. As you know, if you work in communication, you mainly want directional beam patterns as shown on the left towards a user. These are typically not optimal for positioning, and in that case, it is also good to consider so-called derivative beam patterns shown in the second picture. And the combination of directional and derivative beam patterns turns out to be the optimal choice for positioning. The third figure shows so-called random configurations which don't have any directionality, but could be good to localize users if you don't have any prior information. And finally, we've also considered so-called multi-beam configurations, which illuminate several directions at once. Complementing this work on architectures and control, we have also performed work on localization and sensing methods. This slide shows 3 examples. So the first slide shows the channel parameter estimation of a single antenna user with help of a RIS. So in this case, we estimate the delays of the line of sight path and the path via the RIS, as well as the angle of departure from the RIS to the user, and combined, this allows you to localize the user. As shown in the bottom, obviously the path via the base station is the strongest and has the best performance, while the path via the RIS is the weakest and performs and then is the bottleneck for localization. So the localization performance is shown in the middle inset, where we evaluate both directional and random beam configurations. And this shows, of course, that if you know to some extent where the user is, then having directional beams at the RIS towards the user can boost the SNR and thus the localization performance. The final inset shows the ability to sense passive users with hybrid RIS. So these are RISes that are both reflecting and locally processing the information. And here we show that by using machine learning, we can localize and detect several users in an environment. Let's now look at our future plans. So this is 2023, this is the last year of the project. Our main work is now towards the demonstration, where we want to show localization at different frequency bands, such as sub-terahertz, millimeter wave, and sub-6 gigahertz. If you want to know more, you can follow our YouTube channel. You can also find all of our papers and our deliverables at our RISE-6G website with URL rise6g.eu.